Today we're going to move on to chapter 9, and chapter 9, compared to previous chapters, is quite lightweight in terms of maths, and it's probably going to be more of a qualitative type of lecture, but it's about digitisation and about digital signals, and sort of moving from a lot of the theoretical stuff that we've been doing up to now and moving into the real world. So say you have a system where you're going to be testing something in real life, then you will end up getting involved in digitisation. So we're going to talk a little bit first about digital signals. What is a digital signal? How is it represented? There's some equations to do with mean and standard deviation, but you should know them by now. Some of the what happens when you convert a analog signal to a digital signal, and then issues that can arise due to sampling. Okay, and then based on the stuff that we did in the last chapter, chapter 8, on Fourier analysis, I'm going to talk about how that is then applied to digital signals as well, to discrete signals, using the Discrete Fourier Transform, and in particular the Fast Fourier Transform. There's a lot of complicated maths involved in this thing called the FFT. I'm not going to go into it. There's plenty of books out there that can probably teach it far better than I can, but it's worth you knowing about it, okay? Because you may come across it, certainly in things like final year projects, okay? And then applications of it. So like I said, often when you're dealing with a real system, you're going to measure something using a transducer, and often that transducer will be connected up to a computer. The way a computer stores and processes data relies on the signal from the transducer being a digital signal, not an analog signal. You need to convert these analog signals to a digital signal, okay? So the computer can understand it and can read it and can write it. That's the thing. Okay? And this process to convert the analog information of something being measured is known as quantization. And we'll talk about the process that it goes through. And essentially that means that both the time and the signal are quantized to certain specific points, discrete signals. Okay? So when you've got your system, let's say it's a mass spring damper system, and you've got a transducer attached to the thing that's moving, okay, and that transducer will measure its movement, give you an x value in a sense for displacement. Now, if you were to draw that by hand, you would draw x as a continuous line, because between the limits of its movement, your line can be associated with any point along that movement. So you have an analog signal, okay? Doesn't matter what it does, but you can follow that line no matter where along you've got it. But the thing is that what happens is, with a digital signal, you've only got discrete positions that thing can be at, okay? And depending on how many bits your processor can deal with, gives you the resolution, or how closely your digital signal will represent the analog signal. Now, in terms of representing a discrete signal, I've got a couple of graphs here. Here's a signal, okay, of something moving. Along the bottom, you have what's known as the sample number, because, like I said, you take things at a discrete time, and each of those times is a particular sample, okay? And then along the y-axis, we've got an amplitude. This is a dependent variable, okay? And at certain sample numbers, you've got a certain amplitude. And you can see this is one signal, okay, and this is another signal. And you can see with this signal, we've got a mean value of 0.5 and a standard deviation, which is denoted by sigma of 1. We'll talk about those two things in a minute. And then here we've got a mean of 3, which is a lot clearer to see with a smaller standard deviation. Capital N is denoted as the number of samples, okay? And often, there's two ways you can measure samples. You can either go from 1 to n, okay, or from 0 to n minus 1. Now, in this chapter, I talk about from 0 to n minus 1, but for example, MATLAB, which I've used a number of times, that indexes certain points between 1 and n, okay? But like I said, we're going to use from 0 to n minus 1. And so these graphs here both have 512 samples, okay? 512 is one of those important numbers in terms of computing because it's 2 to the power of, I can't remember, 2 to the power of 9, I think, possibly. I can't remember. Anyway, you work it out. So yeah, we've got 512 samples from 0 to n minus 1. Now the mean is denoted by mu, or x bar, okay, with the bar over the top. And that you should all be aware of as you add up all your values and you divide it by the number of values you've got. So here we've got, written mathematically, you've got 1 over n, which is divided by the number of values you've got from I equals 0 to n minus 1 of your values. So you take your, whatever you're measuring, displacement in this case, x, okay, and you add up all those values, you divide it by the number of values you've got the mean, okay, it makes sense. Standard deviation, which is denoted by sigma, and variance, which is sigma squared, okay, is basically a way to indicate how much your signal varies from the mean, okay. You've got xi, which is your value, you've got your mean in here, the difference between the two squared, and then you sum it, and then divide by 1 over n minus 1, okay, will give you the variance. You square root that value to get the standard deviation. Okay, and we'll talk a little bit about standard deviation next week as well, because we're going to be talking about random vibration, so it comes into that chapter as well. But basically it's a measure of how widely varied your data could be. And so if we go back to that graph, you can see that with a small standard deviation, it's quite clear that most of these values are around the mean, because we have a small standard deviation, whereas this one, if I said, what's the average value of that? Well, you can say, well, it's probably above 0, but we're not sure. Okay, that's because the standard deviation is quite large, but you can obviously work out exactly what the mean is in that case. Now, the process of converting an analog signal to a digital signal involves a process of sampling and quantization. This is a two-step process. You sample and then you convert to a digital signal. So here we've got an analog signal, and this is a voltage that varies with time. Okay, for example, voltage is the thing that's measuring, that your transducer is measuring. Okay, and here we've got a voltage, it's around between 3 and 3.025. And you can see that as time increases in seconds, the thing's varying, so it's measuring a position. Okay, for example, that voltage, the transducer converts the position into a voltage. And this voltage can vary. Most things, most sort of sensors that you'll come across will probably be up to 5 volts. But that here measures from between 0 and 4.095 volts. Okay, and that number there, the reason why we've got this here, is if you take 2 to the 12 for a 12-bit digitizer, you get 4096. Okay, and so from 0 to 4.095 means that every 0.001 volt will be one of those values in your digitizer, and that's important when you come across it. So like I said, two-step process. The first step is this thing called sample and hold. And what you do is you take your signal and you divide it up into the number of samples you're taking over that time period. Okay, so that signal that we had, so here we've got a thing that's going to sample every, what does that look like, every second. Okay, and what it does, at 1 second, it'll take the value of the thing at 1 second. It'll then hold that value, and then at 2 seconds, when it takes the next sample, it'll take the value that it holds at that point. What happens between 1 and 2 seconds is not even recorded. And it, in many cases, depending on how fast you're taking samples, it doesn't really matter. Okay, but that's the important bit of information, is that what happens between those 2 times, it has no knowledge of at all, because it's only sampling every 1 second. Okay, a continuous signal obviously will have a signal during that time. Okay, whereas here we're sampling at every second, so you only get a value every second. And so you can see we end up with this sort of stepped thing, because that value that it took at 1 second is held for that complete second until the next value is taken. Okay, so you end up with what was a nice sort of continuous line now becomes a set of discrete steps. Okay, and those values are going to be based upon the value of the voltage that it gave out. Okay, so that could be anywhere along this line. It doesn't have to be at a particular value. It said, well, whatever the value was, it'll take it then. So that's the first step. The second step is called an analog to digital converter, okay, ADC, and that produces an integer value, in this case between 0 and 4095, for each region that's been held. Okay, so we go back to our sample and held graphic. So for each of these particular regions, okay, for each of these things, it'll choose an integer value that's associated with the amplitude, the height of that region. Okay. Now the thing is like I said, this could be anywhere between these two lines. It doesn't have to be a specific point. But obviously between these two lines, we've got 3005, 3006, 3007, and so on. 3005.5 doesn't exist with the integer values. Okay. So if you've got a value that's 3.0055, we'll say, or whatever, or 3.0055. So you're halfway between 2 points. Obviously, that doesn't relate to one of the specific integer values. And so you have a situation where your data gets slightly shifted. So that's what happens, the output from the ADC, is you have a bunch of values that are associated with each of those sort of step values, the step signals. Like I said, if you've got a voltage of, this is at the bottom of page 149, if you've got a voltage of 2.56000 and another point you've got a voltage of 2.56001, they're both going to take the value of 2560. Okay. So although the voltage is different in the analog sense, it's actually going to be the same when you've got the digital signal. So the process converts that's the whole process to convert an analog signal into a digital signal. Once you've got this data, the computer can read and write it, you can do analysis to it, all that sort of stuff, and that's how you deal with the digital signal. Now there are some sampling issues that we have to bear in mind when you're dealing with digital signals, one of which is called aliasing. Okay? Now you may have come across this before, but some of you may have not done so. Now here we've got 4 graphs, okay, of analog and their corresponding digital signals. Okay, the analog signal is the solid line, and the digital signals are the points, the square blocks that are on these graphs. Okay, and the analog signal is the input in a sense, and we've got different sinusoids being input, and then the output is the is the digital version of that signal. And you can see that if you've got a sinusoidal input with a frequency of 0, you can obviously get a constant value, and you can see quite clearly that those digital signals, you can take the digital signals and you can make a pretty good guess at what the analog signal was. So you can go backwards as well. When you increase the frequency, so we're now at 0.9 of the sampling rate, okay, you can see that those dots are lined up along that sinusoid, okay. And again, if you took away the solid line, you could see quite clearly those dots would represent the sinusoid. Okay? So again, you can take the digital signal, you can convert it back to the analog signal, and you'll be pretty sure that that's what you'll get. You go again to this one, so we've gone up again in terms of frequency, 0.31 of the sampling rate. And again, you get a sinusoid, and again, you take the points at your particular sample numbers, okay, and you get a set of values. Here it's a bit less obvious. If you took away the sinusoid, it's a bit less obvious that that thing actually matches the sinusoid, but it does. It uniquely matches that particular sinusoid. No other sinusoid will fill those holes. Okay. But you end up, if you increase the rate beyond 0.5, in fact, is the limit, but here we've got an example of 0.95. You can see that with the same sampling rate, we've got a value. If you took away the sinusoid, you'd end up thinking, well, that's going to be a sinusoid of that frequency. That's wrong. Okay, it's not correct. And that's because this is aliased. Okay, that's what it means. So if your digital signal can be converted back to an analog signal, and it's unique what it comes back with, okay, in terms of, for example, with a sinusoid, that set of data will only fit one sinusoid, and this set of data will only fit one sinusoid, whereas this set of data fits 2 sinusoids. It fits this one, and it fits this very slow one. okay, then you've suffered from aliasing. Now, there's all sorts of examples of aliasing, and ways to get around it. But an example of aliasing you can see in videos. Now, I did find a video earlier on. Now, there are ways to get around it, okay? So, like I said, this is basically explaining what we're doing. If you've got a sinusoid that changes frequency during sampling, this is what's called aliasing. And there's this theorem that was come up by Nyquist, who you've probably heard of, and Shannon, who you may not have heard of, okay, where they say that the signal can be properly sampled, i.e. you can go from digital back to analog and get what you had before, only if it does not contain frequency components above 1/2 of your sampling rate. So, in other words, if you've got something and you're interested in the frequency level up to, say, 20 hertz or whatever, you must sample at least 40 hertz to be able to avoid that problem, that aliasing problem. So for that chopper, the helicopter that we saw, the video, the frame rate, to actually capture what was going on, the frame rate of the video would have to be twice the rotational speed of the rotor. Okay? In that case, it wasn't. The sampling rate must be at least twice the maximum frequency of the signal, and so the equation you could write looks like that, where Fs is the frequency of sampling, so that could be, say, 150 hertz. That's going to be twice the input frequency that you're interested in. Okay? And what you often do is that if you're, say, measuring something, to make sure you avoid the aliasing problem, is you attach in that process, where is that process? This two-step process, in the middle, between the sample and hold and the ADC, you stick a filter in, and that filter will filter out the higher frequency stuff, so you're only left with the lower frequency stuff. The filter, depending on the design of the filter, and that's when the electronics behind it, you can reduce the amplitude or completely eliminate the amplitude of any frequencies above a certain cutoff frequency. Okay? And so what you'll do is, say your ADC is working at 150 hertz, you'll set the filter so it cuts off all frequencies above, say, 75 hertz or whatever. Now, another example of this two-time stuff, the range of human hearing runs from about 20 hertz to 20 kilohertz. And that high end, as we saw right in the first lecture, that reduces the older you get. But anyway, 20 kilohertz is what the human ear can sort of withstand, or can actually hear. Beyond 20 kilohertz, we can't hear anything. But with CDs, you'll notice, I don't know whether you've ever looked at CDs and stuff, or CD ROMs, they record sounds between 0 and 44.1 kilohertz. Okay, well, they're sampled at 44.1 kilohertz because that gets around the aliasing issue. Okay, so the frequencies that you hear are the correct frequencies because the sampling rate is 44.1 kilohertz, which is twice the range of human hearing. Now, with that example, this last one down here, there is actually an equation to work out the frequency of that signal. Okay, obviously this is the input signal, but this one here, you can actually work out what that aliasing frequency is. That's called the aliasing frequency. And FA is the absolute value of the input frequency minus n times Fs, okay, which is the sampling frequency. Now FA is the aliasing frequency, so that's the thing we're interested in. Fin is your input frequency, Fs is the sampling frequency, and n is an integer value whereby Fin and nFs are as close together as possible. Okay, so if you've got Fin being, say, 150 hertz, and your sampling rate is 302 hertz, n would therefore be 2, because, sorry, that's the wrong way around, isn't it? What have I got here? I've got an example here. Yeah, if your input frequency is 150 hertz and the sampling rate is 75 hertz, okay, then n in that case would be 2, because 2 times 75 gives you 150. So the absolute value would actually be 0, okay. Well, obviously if you had 76 hertz or whatever, n would still be 2. If your input frequency increases to 188, suddenly n would be 3, because 3 times 75 is closer to 188 than 2 times 75. Okay, so you have to adjust n. It's got to be an integer, whereby you'll get the closest value or the lowest value for those two, for that term. Will be the lowest value, and that will give you the aliasing frequency. Okay, so in that example where you've got a well, in fact, I've given an example here. If your input frequency is up to 1,000, okay, and your sampling frequency is 492, for example, then you'd have n would be 2, because 2 times 492 is close to 1,000, okay, and you'd end up with a sampling an aliasing frequency of 16 hertz. So you get a signal of 16 hertz for a frequency of 1,000 hertz, okay, if you went back the other way. And like I said, to avoid aliasing, you often stick a filter in your system to try and solve that problem. So that's the basics. We'll then move on to the Fourier analysis of discrete signals. Now, as we know from last chapter and from chapter 4, for every time domain waveform signal, okay, there is a corresponding frequency signal. Okay, frequency domain. Moving from the time domain to the frequency domain is what Fourier is all about. And so you can decompose a time signal into a series of sinusoids, and the same principles apply to discrete signals. So if you've got a bunch of values for your discrete signal I guess in the sort of time domain, because you've got it against samples, you can apply the Fourier transform and you can get the frequencies at which that thing could be represented. Now, coming up are a bunch of equations. I don't expect you to remember them, and to be honest, you won't need them. Okay, but it's here for completeness. Okay, again, like we had with the continuous signals back in chapter 7, lowercase letters mean the time domain, and uppercase letters mean the x domain. We've got square brackets here instead of curved parentheses, and that indicates that we're dealing with a discrete signal, not a continuous signal. N is the number, the sample number, so that's the time domain, and k is the index number, which gives us the frequency domain. And that's the equation, okay? It's a little bit similar. We've got a 2 pi divided by n and multiplied by k in there instead of omega, but it's the same sort of thing. And then obviously you can go the other way using the inverse of that complex. And that's called a discrete Fourier transform, okay, because it deals with discrete signals. Now, there's lots of different ways of dealing with discrete Fourier transforms. Okay, and one of the ways that we're going to talk about is this thing called the Fast Fourier Transform. And you may have heard of FFT before, Fast Fourier Transform. It's one method of solving this problem, of getting the frequency domain from a discrete signal. Okay, the big advantage of the FFT versus other types of discrete Fourier transform is it's very, very efficient in terms of the computing power, and as a consequence, it's extremely quick at doing it. Okay. Like I said, it's quite complex, and I'm not going to go into it here in terms of the maths. But you have to remember that with FFT, the sample number must be a power of 2. So 2 to the power of something. So for example, here we've got, if your sampling rate must, say you're measuring a system with 100 hertz frequency that you're interested in, okay? Then the sampling rate must be 200 hertz, because it's got to be twice it. And if you're using FFT, it's got to be 256. Because that's above 200, and it's a power of 2. 2 to the power of 8 is 256. Now, I skipped over a slide here, which is important. Frequency resolution. To perform a discrete Fourier transform, you need a certain number of samples to actually work it out properly. Okay? And so there's an equation here relating the frequency resolution and the sample frequency, okay, to work out how many samples you need. And so, for example, if your frequency resolution is 20 hertz, the sampling frequency needs to be 500 hertz, because obviously our signals that we're interested in are perhaps 250 Hertz. Okay? The number of samples required is 25 samples. And like I said, with a fast Fourier transform, this value will have to be 2 to the power of something. We'll go through an example of this later. So that's the fast Fourier transform. And the application, like I said, is determining signals' frequency spectrum. So here we've got a measured signal. This could be again, a position or something. It's been driven by a certain, something in particular, okay? And this is the signal you get. It's quite random. Looking at that, you can't make any sense of it, okay? But if you did the Fourier transform of it, you get something that looks a little bit like this, okay? And this graph here, you can see quite clearly that we've got you've got a bit of noise at this end, and sort of some white noise along the bottom here. But at certain points, at certain frequencies, because you've got frequency on the bottom, you've got a peak that appears, okay? Some peaks. And you can see, by performing the Fourier transform of this signal into this signal, you can see that the dominant frequencies is 13 Hertz, and then 26 Hertz, which is 2 times 13, is a harmonic, and 39 Hertz, which is 3 times 13, is a harmonic. And so the dominant frequency in that signal is 13 Hertz. Now the 60 Hertz thing here is possibly because it was plugged into an American power supply, which AC in America operates at 60 Hertz. And so sometimes, if your transducer is plugged into a power supply, you might get a peak at 60 Hertz as well. And that's the key to this Fourier transform stuff. This is the same method applies to the last chapter. Remember I talked about, right in the first lecture about Fourier transforms, about music, okay? Well, this thing could be a sound wave, okay? Measuring, up on the y-axis you'd have pressure, okay? And on the bottom you'd have time, okay? And you could measure, if it was possible, to measure the pressure fluctuations as sound is moving through the air, okay? So you're measuring the pressure fluctuations. Obviously, just by looking at that, you can make no sense of what sound that is, okay? Because we don't listen to sound in terms of how it appears in terms of pressure versus time. But you take the Fourier transform of that signal, and you're going to get a frequency, and a frequency matches up to a pitch of sound, okay? Which we do understand. You can understand pitch, you can understand high pitches and low pitches, high frequencies and low frequencies, and those frequencies are hidden in that graph of pressure versus time. Okay, so it's the same process that's going on here. It's just that like I said, you can apply all that stuff to discrete signals as well as digital signals. As well as analog signals. So that's actually it in terms of the theory of this chapter. Like I said, it's quite quick, and it's relatively straightforward, and it's qualitative as well. But it's worth sort of appreciating that, especially when we start looking at the next chapter. And in terms of, like I said, if you're doing a final year project that involves something that moves and you're measuring how far it moves, you're going to be dealing with these sort of issues, okay? If you've got something that vibrates backwards and forwards, might have a random signal, okay? You have to bear in mind that when you're sampling it, okay, when you're trying to measure that thing, you need to make sure that the frequency you're interested in is half of your sampling rate, okay? If your frequency and the sampling rate are about the same, you're going to end up with possible aliasing, which is obviously a bad thing, okay? So say you're using the Cortical rig in the dynamics lab, measuring its motion, okay, of the structure based on a road input. You might have to make sure that your sampling rate is twice the frequencies that you're going to be looking at, okay, or fast enough.